Coming up in the next episode of Baya Systems' Tech Threads podcast, we're excited today to host Raja Koduri, who's been at the forefront of compute at tech world's most iconic companies like Apple, Intel, and AMD. And joining him will be our very own Dr. Sailesh Kumar, co-founder and CEO at Baya Systems. Together, they'll explore the emerging intelligent compute era.
Welcome to Tech Threads, Weaving the Intelligent Future, the podcast exploring the fast-paced world of technology. In each episode, we dive into the latest innovations in data movement, AI acceleration, and the transformative potential of chiplet technology. Join us as we explore the breakthroughs that shape the future of computing and hear from industry experts on what's coming next in the tech landscape.
Hello, and welcome to Baya Systems' Tech Threads podcast. I'm Nandan Nampally, Chief Commercial Officer here at Baya Systems. And today we have a couple of real stars that will be exploring the emerging intelligent compute era with us. Firstly, we have Raja Koduri, who is the founder and CEO of Mihiri AI, as well as a stealth hardware startup in the Silicon Valley at the moment, where he's spearheading groundbreaking advancements in AI, graphics, and supercomputing. His remarkable journey has taken him from humble beginnings in India to leading roles in some of the world's most iconic technology companies, including S3, ATI, AMD, Apple, and Intel. And Raja there has defined or redefined actually what's possible in high-performance computing, from GPUs that power modern gaming to professional graphics to energy-efficient mobile solutions that transform smartphones into the tools that we expect today in the digital age. He's also led monumental achievements, including the creation of the first 10 exascale AI supercomputer in the United States. And of course, he continues to innovate at the intersection of AI and visualization technology. And not only is his genius kind of with deep roots in semiconductor and VFX industries, but he's also leading Makuta Effects, a studio renowned for groundbreaking contributions to Indian cinema with masterpieces like Bahubali and RRR, blending cutting-edge visual effects with artistic storytelling to captivate audiences. Well, Raja, welcome to the podcast.
Thank you, Nanda. I'm excited to be here.
Great. And joining Raja is Sailesh Kumar, who most of you know is the CEO of Baya Systems. Obviously, Sailesh is a seasoned expert in SoC, fabric, and networking, and has had an extremely advanced career in algorithms over the last couple of decades of experience. He pioneered several high-impact industry-first technologies, including the 400 gigabit network at processor at Huawei, software-defined fabric at NetSpeed, which he founded. He was very critical to Xeon architecture and transportation at Intel. And of course, now he's defined a new startup for software-defined chiplet-ready networking. Welcome, Sailesh.
Thank you. Super excited to be with Raja.
Yeah, I mean, clearly this is more of a reunion of sorts of kind of two experts have been at both companies together as well as seen each other in the industry. So let me start by asking both of you, and I'll start with you, Raja, on your experience in the world of compute over the last few decades. Can you just take us through your journey and kind of tell us how you've seen it evolve?
Yeah, sure. Again, super happy to be, here with Sailesh on this podcast too. By the way, in the world of, computers, architecture, and especially in this bubble we live in called Silicon Valley, they are, less than, probably two handful of people that are here that can, that I can talk about architecture, and Sailesh is one of those few minds, whether connecting from software all the way down to how the bits and bytes move in the system. So it's always a pleasure to be nerding out with him on any topics. But in the broader topic of computing, fascinating, 30 years for me here in the Silicon Valley, and the I'll give you just my personal perspective, just being in the graphics side of the equation, right? We started building this graphics chip for 2D acceleration, right? What you're seeing currently on the screen, right? Windows bit we call them, and then some video and image processing, and then 3D games. Caught our attention and said, let's do 3D graphics. And but all along, the thing was there was always, hey, you have reached the limit of computing. Like hey, graphics is good enough, and it got integrated into the CPU, and that's it, right? It gets commoditized, and you guys are out of business. So that we are out of business was there, it was 3 years away, right? Every time, right? From mid 1990s to, until kind of the last 5 years of AI happened. And it looked credible. It's not just some random people saying that, like a very informed people declaring that, and it didn't happen. So one thing, my takeaway I tell companies is basically, don't look at the technology, don't look at the problem or solution you're building. Look at what is the workload, right? If the workload domain is highly scalable in the sense that if you throw more compute on this workload, the workload gets better. If you are in domains like that, there is no end in sight, right? It's basically you'll keep, the need for your compute, whether it was graphical compute, now it kind of transformed to this big matrix array compute, and there is still no end in sight. And that's the fascinating part for me, just the 30-year journey. We always thought, we are at, 5 years before it's, we are, every computer is fast enough, everything is fast enough, and the value shifts someplace else. And sitting here and saying, oh, we are nowhere close to that, right? Is an amazing place to be.
Well, that's quite impressive, right? And I think you've also seen, from my perspective, I see this as, if you go back 60 years, it was punch cards as input, then it was keyboard and screen as input. Then in a lot of what you did in your early part of your career, it was trying to take not just the traditional one, but gyro and camera, etc. So the phone started pulling together that compute. You started getting into now augmented reality type compute, and now we get into true intelligence type compute. At each stage, it feels like there is more compute, different kinds of compute, and the hunger is endless, right? You're always going to go further, and you have to be smarter to support it. Now, that kind of gives me a chance to bring in Sailesh as well, because I think in a lot of these evolutionary paths, the network is the computer rather than a computer as a network. So I'd love to kind of hear your view on that, Sailesh.
Yeah, sure. So before I add my color, again, I'm super excited to be with Raja. He is a super, I will say one of the biggest visionaries in computing that I know personally, and I'm so lucky to be to know him. I mean, he has been redefining compute for 3 decades now. Now, there's a craze about GPU, high performance parallel computing, and new ways of doing computing beyond CPUs. And he has been driving this transformation for last 2 decades. He was the force behind, driving the whole GPUs architectures at Apple and then AMD. And then he was leading, big, discrete GPU projects at Intel as well. So now I think, we are in the AI age where GPU is driving a lot of compute, a lot of innovation. And Raja, oversaw all that. He has been on the forefront. So I will actually say Raja is, literally, on the same level as Jensen, who is getting all the limelight today. So super, fortunate, to be, to get the chance to work with him, nerd with him out. So So Raja is more of a system software architect. He starts thinking from the system software and then go all the way to the hardware microarchitecture level. How do we build that system at the hardware level? So he has that full stack view of the system. My view is somewhat more limited. I look at the interconnection of various components, and where I think we sort of intersect really well is, as that systems are scaling and becoming really large across multiple packages, multiple chiplets, and also heterogeneous compute is taking off now because different workloads require different types of compute. You need a combination of CPU, GPU, accelerators. So in this new era of compute, one of the critical piece to scale is the network, because you have large number of components distributed across multiple chiplets, multiple packages, and lot of communication has to happen, a lot of data movement has to happen, and all this data movement has to be high bandwidth, low latency, and also in many cases cache coherent when you have caches to accelerate the data access. So this is a fundamental bottleneck that we have today. And my entire background is really I have been trained to solve this problem. Did my PhD in networking, worked on network processors, worked on extremely high bandwidth, highly scalable architectures, and then started to work on chip fabrics, and that I have been doing for last 1.5 decades now. So it is really super exciting that all this background that I have in networking, fabrics, now, is actually a real problem. And I get to apply all of these to build, highly scalable systems, highly scalable architectures, which we really need now to solve the fundamental, transition in the compute problem. So I'm really super excited. And, I to first witness this transformation in compute and then contribute towards the building one of the fundamental pieces, core pieces, which is the data movement in this new paradigm.
That's a fair statement, right? So if we think about it from the way Radha described it, it's really no longer about a widget. It's no longer about the network. It's not just about the software. You have to start thinking differently, right? So we are at an interesting point, I would say. So being the visionary that you are, Raja, I'd love to kind of understand, are we at an inflection point now? Or is it just another one of those kind of stepping stones that you alluded to in your past, every few years we see it? And if so, what does the next wave of computing look like?
So, building on what Sailesh said, right? It's really interesting. The first, I'd say, 2 decades, at least of my, journey, it was a lot about integration, because like Moore's law was kind of king. We're still riding on the kind of, both Moore's law and Dennard scaling. So, we're taking problems and saying, okay, how can I integrate all onto a single die? Right? So a lot of innovation was integration, right? And now we are in the scale era of computing, right? So yes, we integrated, those are like an integrated chiplets are available, but the size of the problem needs scale, right? It is scale. Okay, so all technologies, software, systems, silicon, all come to scale. And what scales, to scale, you need that, what we call a fabric, what we call a network, what we call, that is the key, so the how you connect these things up together and how you productively have them, literally, when I have, 2 things instead of 1, you want twice the performance, not 1.1 times or 1.2 times the performance, right? So where we are now and what we have already entered in the next 10 years, the importance of scale, right? It shifted from integration to scale. Okay, so that's kind of how I would connect the dots, and so the AI, just take this into consideration, right? Basically, the compute requirements of AI models is roughly 3 times annual CAGR, right? And the bandwidth and memory capacity requirements are also going at the same rate, three times, right? And what a single chip is giving you, right, on the annual CAGR is 1.2 times, right? So the demand far exceeds the supply right now, right? So even if I can buy all the chips, and the stuff, I'm only getting, on a per chip level 1.2. So I have to use multiple chips to meet the demand. Okay. And now when I use multiple chips, if I'm losing like the scaling, right? So I'm inefficient scaling, very, very expensive, but they're doing it, right? So the first generation of AI supercomputers that are put together, right, are I call it kind of, yes, we did it. Like, they're selling a lot, right? All the stuff, but they're not yet very efficient. So the efficient scaling, when I can linearly multiply this stuff, it's going to happen. So, and there is no end in sight, like at least till, 2030, the scaling of compute needed, the scaling of bandwidth needed, are all coming. Now, there is one interesting side effect, though, right, is that software optimizations where on a same compute, same bandwidth, okay, that I have in a system, every year, software guys come up with new approaches, new algorithms, and they improve overall, the workload efficiency by 3x as well. So if you multiply all the numbers of like the demand versus supply and software algorithms, the hardware industry, right, is growing at 2.5x. So it's actually like really interesting if you take NVIDIA revenues, okay, for the past 3 years, it is directly corresponds to like, this doubling of the stuff. And you can also see that they themselves are unable to meet the demand. If they could make more B200s or whatever GPUs they make, their revenues would be higher. So they are not actually demand constrained, they are supply constrained because they're not completely meeting this stuff. So there are other players, they're getting some percentage of the thing. So this thing is like, I have never seen in my 30 years where a company goes from 30 billion to 60 billion to 130 billion in 2 years, right? 30 to 60 in 1 year, 60 to 130 in the year. And I think they're well on track to cross 200 billion, right, to the next financial year. So it's kind of crazy. And the total industry is on path to $1 trillion of revenues, not, market cap or like, PE stuff, actual solid revenues by 2030.
Yeah, it is. I think you captured it well, right? It's scale is the key issue, whether it is in terms of silicon or capacity of software that needs to be run, kinds of workloads that need to be run, services that need to be run. We are supply constrained. So I'll kind of turn it over to Sailesh as well, because one of the key statements you've consistently had is it's about scaling. What we're seeing in the market's about scaling, but would love to get your take on this as well, Shailesh.
Yeah, absolutely. So, what the insight that Raja just provided, that chips themselves are scaling at 20% CAGR, but then overall compute demand is scaling at 3x CAGR. I will actually say that there is really no limit. It's just, as you pointed out, it's supply limited. So if we can increase the compute capacity, overall system compute capacity by 10x, we will take it. Because till we hit AGI, we will keep scaling. So that's the path we are on, and on this path, in my mind, what is the bottleneck? The bottleneck is it scaling, ability to scale, or is it ability to write a software that can leverage all the scaled up or scaled out hardware? Perhaps it's a combination of both of those two. The software, I'm sure that software is already being addressed by many players, including Raja. He has lots of amazing ideas about how to democratize the software development for these scale up and scale out heterogeneous compute architectures. where I focus on is the scaling of the system. How do we scale the systems efficiently? And today, the way scaling happens is it happens, around certain proprietary protocol and standards. Like NVIDIA, for example, is the most dominant scale-up architecture, where they have NVLink standard that they use to scale up single socket to many sockets and provide a unified view of memory to the application. It's a proprietary standard. There's some, open standards that are coming as well, like UA-Link, Ultra Ethernet, but they are somewhat new and still have to take off. One of the things that I see that happens is, as these systems are, being designed at scale, is the fabric is usually designed in a very sort of one-off custom way, that for each particular type of system, let's design a fabric that's optimized for this. No one is looking at a holistic view of, can we define a fabric architecture and power it with the right set of parameters, right set of configurability, and right set of software tooling, that the common fabric architecture can be tailored for different types of applications, different types of workloads. Training systems will have different types of workload, different types of traffic pattern than inference. Within inference also, if you slice and dice, you may have different types of workloads, different types of communication in different deployments. So how do you build a fabric that is not just one-off design, but rather a reusable design that can be customized for every application in the most efficient way? So if scaling is indeed the bottleneck, then that is one problem, that can definitely help in avoiding that bottleneck. And that's where I think Baya is focused on, to build a highly configurable, software-defined fabric that can scale beyond a single chip and can allow you to build a highly customized solution. So that's the scaling story that we are pursuing, and also in terms of what are the actual mechanics of scaling, there are different thought process in the industry. People keep debating between scale up and scale out. Like in the CPU days, scale up and scale out, the boundary was very, very clear. But now in the new computing paradigm, the boundary between scale up and scale out itself is, not very clear, because, there's overlap between those two. And even the standards like, UA-Link came as a scale-up protocol. Ultra Ethernet was more of a scale-out, but even those two standards are coming together. So in general, the scaling itself is, going beyond sort of fixed, load store semantic scale-up versus message passing scale-out, but, is becoming one unified scaling approach. So in this new paradigm, I think, if once we have these new standards, become more popular, it will actually be cool to, come up with a fabric solution that can scale to not just, thousands of sockets, but, potentially millions of sockets, and can support multiple tiers. Because once you scale to that level, you have to start to create hierarchies. You have to have, first, level nodes, then you have to have second level nodes, domains. So those are the sort of areas where I'm super excited about. And one of the things we are seeing, at least in the industry, is that there are a lot of new startups coming who are trying to reinvent the scaling. These are the startups that are building custom silicon to create solutions that can connect thousands of nodes within a rack, and then go beyond that and connect the multiple racks with hierarchy. And these are the people who are building multiple terabyte per second bandwidth or petabyte per second bandwidth systems with thousands of ports switching. So when I see all of these new types of architecture coming up to solve the scaling problem, I get super excited, because we are working with some of these people, and when I see that they are excited about using our technology to build these highly scaled systems, then at least we see a path where we can go beyond legacy scaling using Broadcom switches and start to talk about true scaled architecture.
Mm-hmm.
And then the other aspect of that is the software. How do you write software for these highly scaled architectures with multiple tiers, and still give programmers a high level abstract Python APIs to program. And I think that's another problem that has to be solved, because software has to keep up with the hardware, and that's the problem that Raja is trying to solve. So maybe Raja should add some more color to that, because I believe, like, if you talk to anybody in the industry, what is the biggest strength of NVIDIA? They will say CUDA software. All the software libraries they have built, all of that's their real strength, and that's where the bottleneck is. So as we scale, I think it's super important that we solve the software problem as well, and provide the right abstraction level for the users to be able to use that hardware efficiently.
I think you've got to a very interesting point to where I was going to preferably go anyway, which is, if you now look at these very evolved, very scalable, potentially very tiered systems, there is a question of how do you design them well, right? So is there something that changes in the way we actually think about systems? Are we thinking from a service first perspective, a software first perspective, and how does hardware scale? So I'd love your take on this, Raja, on how system design, especially including, what are the way to enable software, as Sailesh was saying, how should we be thinking of systems in the future?
Yeah. First off, the limit for scaling is actually, not even AGI, in the sense that it won't stop after AGI, because, that we are on a trajectory that there will be, before, market sizes were limited, generally based on, there are 6 billion or 7 billion people in the world, and they multiply how many people can you get, right? How many people will buy your solution, or how many people will use your solution. It was human size limited market. Now, by 2030, maybe even before 2030, you'll have 1 trillion agents running on these networks, right, utilizing all this stuff. So that will be augmented by these agents, whether they are agents running, in virtual environments, or agents sitting inside a robot, or physical, the things that you can see physical, right? So the TAM from a user perspective is, gotten 1000x the usual market TAM. Okay, so the scale is, I think, if you're limiting to, hey, when we train the AGI model, it may stop. No, the user scale is just, we are, not even touch the the starting point of the user scale for AI yet, right? It is still very small percentage of the 7 billion users, but that is not the stuff. These agents will be in trillions. Okay, so that
that's just a pretty amazing perspective right there, right? So don't think about it as a TAM of users or clients. It is actually now virtual users or intelligent users that are no longer human. Wow. Yeah, sorry, continue.
So in terms of how we think about it, right, I've been thinking about this. So there is a, very famous, I think, a blog post or a thing that a famous AI scientist called Richard Sutton wrote. Rich Sutton, it's called The Bitter Truth, right? So the essence of his thing is that, hey, for, several decades, from 50s, 60s, the AI community was looking at AI as this very sophisticated, they're trying to come up with very intelligent ways, right, to do AI. And his thing was, in the end, very brute force, blunt techniques that just utilized a lot of compute, will people say very inefficiently, or they're needing so many multiplies and adds, literally, right, 10 power 15, 10 power 18 scale multiply and adds to just answer your stupid chat GPT question, right? The stuff, people say it is brute force, right? And not very elegant relative to some of the approaches that the AI scientists were kind of, still, there's still some pursuing, that there should be a more, a brain doesn't do so much stuff. Our brains are much more efficient at stuff and all that stuff. So there is that whole thing of, the bitter truth essence is simple, dumb things scale. Okay. And I think I think about that for the network fabric and all, right? The current, like, the switches and all the high-end switches are all very sophisticated. They have, fancy, right, routing protocols, and like try to optimize for tail latencies, and, get, to be, they are already very sophisticated. But the scale we need, is there a simple, so the simple thing, somebody who goes after a simple thing that kind of, easily, multiplies, right? And presents a simple interface to software, which is kind of the workload, is, my sense is what is going to win, right? The simple stuff, even if it is not super smart or something, but its complexity comes on how easily it scales, right? Its magic is how easily it scales. And if you look at why GPUs succeeded, it is that particular simplicity there was, right? I remember it was 2009. I just joined Apple, and there was a discussion inside Apple if we should adopt Intel's Larrabee architecture, right? Which was kind of a Intel's competitor to the GPU, but it was because it was a CPU core, and CPU core stuff. It does much better on sparsity and sparse workloads and kind of complex parallelism. You can express better on that. Whereas GPU was dumb, simple parallelism, right? You dense matrix multiplies dense stuff. So if you got very fancy parallel algorithms, GPU sucked, right? And to some extent, it still sucks, right? It hasn't evolved very much. It's a very kind of, simple-minded scale solution. Whereas this CPU-based multi-core, many-core like approaches can do more sophisticated algorithms. But, Jim Keller famously I call it the Jim Keller bucket diagram. And he said, Roger, it was in 2009. He said, hey, there is single-threaded applications. There is embarrassingly parallel dense, workloads. And there is a valley of death in between, which is this kind of, sophisticated sparse stuff. And he said for 30, 40 years, because it's a good computer science problem, the sparse stuff, all the intellectual brains work on it. But really, the whole workloads are either here or here. There is nothing in between. He said in 2009, by the way, right? And I call that the, Keller's bucket diagram from then on. And it still is true, right? It's basically like simple things scale, right? In the single-threaded world, user scaling, right? Yeah, all of cloud is like, it scaled because of users. But the single workload itself in CPU world doesn't have much scale, right? You're just, a lot of many single-threaded workloads just, occupying the cloud. And in the GPU world, simple, basically huge data parallelism, right? The same instruction running on like, a whole pile of data. So I don't know. I'm not a network scaling, whatever expert. I just kind of, just in the, just brainstorming or like in the stuff is that the scale we need can be too sophisticated or like, if you make it too sophisticated, it'll be too complicated, right? It should be something very easy to like, I just say, hey, I need 1 million of this. And I just dispatch a work on this stuff and it just scales and works, right?
No, I think that's a fair point, right? But at the same time, in order to design all of that and to make it simple,
that's where we come in, right? Sure. That's
exactly.
My thing is, make it simple for the consumer, right? What you're doing is high art, right? Like, underneath, right? But it should be very simple to consume for, whether it's a silicon guy, system guy, software guy, particularly, right? Is that, hey, you just do this and, dispatch your matrix multiply and just make it as big as you can. And it just kind of scales to 1 million systems. Beautiful thing.
Perfect. And I think what you're talking about very clearly is, hey, we need to make it simple for the user. So we're going to create the layer that allows them to do all of that. But interestingly enough, underneath, the hardware also has to be smart enough to kind of be built in a way where it delivers those kinds of scalable solutions. And that's, I think, where I think Sailesh convinced me to come here specifically with that vision of how do we do that from a a compute systems perspective. So I'll let him weigh in and tell his story.
Yeah, I mean, I think Raja put it very simply that software programmers want to see a scale system where they don't want to deal with the complexities of scaling. What is the semantics in which various nodes communicate. All of that should be hidden. And that's the job of networking. But then there's physics that come in play as well. Like when distances are different, there's going to be latency differences. When you go across, chiplets or across packages, there's going to be bandwidth discontinuity. So how do you hide all of that is challenging. I mean, if physics was not a limit, then yes, you can scale. And that's where I think hierarchies come in and all of that, where you have different tiers and you have different latency properties within a tier and bandwidth properties, and once you go across tiers, you have a different level of service. So, I mean, those are the pragmatic things that need to happen. But still, if we can abstract all of those in a very simple semantics, that you have this 2 million node system where I have three levels. First level has 1,000 nodes each, and they have all exactly same latency and bandwidth properties. And then you go to the next level where you have another 1,000 of these clusters, and they have certain bandwidth latency service guarantees. If you provide that level of service and that level of abstraction to the programmers, that definitely will help. And also, the lower level details can be all hidden under driver firmware layers. So application will basically not see any of that, and can work in a 3-tier namespace type of environment. So that's where I think all these protocols that are coming up, scale up, scale out protocol, that's what they're trying to kind of solve. That let's give a very simple namespace, and then the implementation will guarantee certain bandwidth and latency properties. So that's how I think it's hopefully it's going to evolve, and that will be very simple and scalable architecture. Having said that, one thing I have seen is that you start with a beautiful architecture always, and then somebody will come and say, oh, for this particular application, if I add this complexity, then I can get a local maxima where I can beat the performance of my competitors, and they will implement that custom thing, and then they will get a 20% performance, and then they'll start to win, and therefore there's going to be more investment in that space, and then you are off your trajectory of simple and beautiful architecture. So those things happen all the time as well. And we will see. I mean, and that's where I think visionaries like Raja or Jensen or Jim Keller, these guys need to make sure that we are on the right trajectory as we scale these systems, because I think AI requires way more scale than where we are, and the more scale we create, the better. I think the more closer we get towards AGI. And as Raja said, the scaling doesn't stop there. We'll keep scaling beyond that point as well. So I think it's important, as Raja said, that simplicity is the key. And also abstractions are the key, in the sense that there may be complexity in the network, but it's very important to hide that complexity and provide a simple abstract interface. So the standard principles, layered architecture, abstractions, all of that are super critical as we build the new compute architectures.
Nandan, if I may just add a couple of things to Sailesh's thing, is that software can deal with constraints. What I mean by that is, if you see the success of the GPU programming model and CUDA and all, it is successful because it has constraints, right? It's like, okay, you can program, but here are the constraints in which your code is limited by, as opposed to the CPU programming model, which you can say is bit unconstrained, right? It followed a lot of CPU programming model with constraints. You can say GPU programming model is a CPU programming model with constraints. And then, rest is history. It scaled, delivered performance. So you can, for this, vision of million computers kind of, just simply scaling with one single piece of software, can be achieved with passing some simple constraint to the software guy saying, oh, if you structure your code this way, what you're very familiar with, but like, if you packetize this way or you put in this container, if in this stuff, it will scale. They will do that, right? I mean, don't underestimate their ability to adapt to kind of do the stuff. Now, there is this, at any given point of time, there is always this desire that people will optimize, right? They'll go to the next level of detail, to extract sometimes last 10%, or sometimes, they may even find 10x opportunities on a given system, like, the DeepSeek example, right? And the stuff, right? But funny enough, if you double click on all of this stuff, right, and it's not actually that complicated, there are three things that happen in a system, right? Three major optimization, three things, right? That I have my compute cycles, let's call them A, right? I take A milliseconds or microseconds to do compute. I have B, which is my cycles to move data from my DRAM into compute, and C, that cycles I take to move data between my node and the next node, interconnect network node, right? You have A, B, C, right? Every workload is a combination of this A, B, C. And the worst you can do is A plus B plus C. Your total time is A plus B plus C, right? And the best you can do is your total time is max A, B, C. Okay, so the entire optimization problem really comes down to both with the software abstractions and the hardware abstraction. Have we given the ability for the algorithm developer or software developer to attain max ABC, right? So that it's not A plus B plus C, right? And that's the art of basically the software hardware co-design. Is if they can always be in the max ABC, not A plus B plus C, you're done your job. Now, once say in max ABC, if A is my bottleneck, right, which is compute is bottleneck, let's say for that workload, and I can reduce compute by different algorithm, reducing, or increasing my GPU flop count and all that stuff. My bandwidth increases, my net, my interconnect increases. So A, B, C independently will be, scaling, with technology architectures. But the system level thing is this between if you profile and build NVIDIA systems or anybody, the reality lies between A plus B plus C and max ABC, right? Somewhere in the thing. So the ideal best I could achieve is max ABC, and that's how I look at this problem.
That's an excellent way to put it. In fact, after all this nerding out, it sounds like the next generation compute is as simple as ABC, as long as we hide the complexity.
Yeah, it is in many ways, right? If you can look at the problem that way, it actually, lots of things get clarified, is right, especially for Baya Systems and the fabrics, a lot of times, right, the C, let's say, right, you have an impact on, but sometimes you find in a particular system and a particular workload is so bottlenecked by A or B that you make 2x improvement, but the end benefit is in C, and because the B and A are just big monster sitting there not moving, right? And
no intent. Basically, we're saying we have to keep improving A, B, C independently, but also then try to get to max ABC. And that's our goal.
Yeah. So if the overlap and latency coverage isn't there, then it becomes A plus B plus C.
Exactly.
Right? So that's where the magic of the kind of the latency coverage and that I can overlap compute, communication, and memory, right? If you can't overlap in the architecture, and that's where some of the intelligence in the fabrics and some of the the facilities you provide help me as a compute provider or a software provider to overlap A, B, and C.
Indeed. So I think that kind of wraps quite a bit of our deep tech talk. And clearly, I'm quite excited and fascinated by this next generation of systems that you're looking for and envisioning. We're trying to help enable. But I'll kind of then bring on the fun part that's going towards AGI. So I'd love for you to kind of define what AGI means to you, and do we see it in our lifestyles?
Good question. It's what does AGI mean to me, right? To me that this computational thing being a my personal sidekick, I call it, right? That gives me that my superhuman abilities. That is what I look forward to, right? Is that but I think the ones that will work and kind of as humans is that we always need this notion or the illusion, I call it. Human likes the illusion of control. Okay. So, both, and it's a big philosophical statement in your life, in your thing in there, that we actually don't have control, but we just constantly,
We assume
strive for
or presume.
the illusion of control. And same thing is going to happen with AI, AGI, that, we want to, we will, embrace it when we say, oh, I can control it, right? Even though it may be from an intelligence point of view, way smarter than me, right? Or has way more information than me, but it is in my control.
I think it's an interesting, I think the way you said it makes sense as to that illusion of control. So instead of, like, if you're in control, you have a sidekick. Mm-hmm. If you're letting it be, then it's an extension of yourself, right? So it's you as opposed to having a separate sidekick that's out there to help you. And I think you made that distinction very clear. So I think we've had fun discussing this, and I'm sure we'll talk about this again, but I can't believe you've kind of run through 40 plus minutes having a nerd out and enjoying it while we're doing it. So I'd like to thank you, Raja, for coming on board. I know you're very busy, especially changing the world on all parts. So your time is valuable. We appreciate it. Sailesh, as always, thanks for joining. Thanks for adding perspective. And we'll see you later.
Thank you. Thank you, both.
Thank you.
Thank you for listening to Tech Threads, Weaving the Intelligent Future podcast. Join us monthly for insights into the evolving tech landscape and the future of chiplet technology. If you enjoyed today's episode, don't forget to subscribe and share it with your network. And stay tuned for more expert discussions. Let's weave the intelligent future together.